Well, as Monty Python says, now for something entirely different.
I was thinking the same thing.
So we're going to switch from the world of the very practical of fighting wildfires to the frontiers of computers. We're fortunate to have Geordie Rhodes here, who's the founder and CTO of D-Wave Systems, a Canadian startup that has made progress on taking the ideas that we've heard about in quantum computing for a number of years now and come up with a commercial implementation of that. So I thought what we could do is maybe start off by asking you, so what is quantum computing and how does it differ from classical computing? And just for the lay audience.
So allow me a digression before I answer your question. So if I take an object, like say a pen, and I let it go, we have this concept that has been built in us since we were small. We know what's going to happen. It'll fall. So if I drop it, there it goes. If it did anything but that, we would be very surprised. So the mathematics behind the intuition of how the world works is generally described as being physics. So in the 17th century, say, the mathematization of physics really began in earnest. And out of that process came a very good description of the way the world works. So we have a very good mathematical framework for understanding pretty much everything that's of human scales. And this description framework is called classical physics. Roughly at the turn of the century, not this last one, but the one before that, it was noticed that certain aspects of the way nature works didn't conform to this framework. And they were small things, mostly seen in research lab types of settings. But those observations triggered a revolution in the way that we understand the way the world works. So in the early 1900s, a framework was developed or discovered which is called quantum mechanics. And quantum mechanics purports to describe nature at a very fundamental level, and perhaps the most fundamental level there is. So this set of laws governs the behavior of all things. It's a common misconception that quantum physics and quantum mechanics is only about small and cold things. That's not true. Quantum mechanics describes the behavior of everything. And it turns out through a process that's now fairly well understood that when things become big and hot, a lot of the unusual features of quantum physics are washed away or somehow they lose the ability to easily perceive them. So back to the question, what's a quantum computer? Computers are constrained by the laws of physics. When you write information on something or you build a machine to process that information, what you can do with it can be no more than what the laws of physics allow you to do. So pretty much every computer that's ever been built in the history of man operates at the fundamental level on classical devices, the things that obey the rules that are very similar to the way the pen falls when I drop it. A quantum computer is a machine where the fundamental information and the processing of that information is done on devices that obey the laws of quantum mechanics. So these things can be very small and very cold. They can be built out of exotic materials. There's roughly a dozen different ways people are trying to build these machines today. I have some pictures in this slide deck of what ours looks like, because it's quite an impressive machine, both in concept and aesthetically. So that was the long answer. The short answer is a quantum computer is a machine that harnesses the language of nature at the most fundamental level to gain, in some cases, extremely impressive performance gains over conventional computers.
So how did you decide that you had gotten to the point that you had an implementation of these ideas that you could actually take commercially?
Well, when the company was first founded roughly 10 years ago, we certainly weren't at that point. So this effort was begun a long time before we had a specific idea of how to implement the machine. It was originally, the company was founded based on the speculation that the timescales over which the science would progress to commercialization were roughly 10 to 20 years. So that was 10 years ago. And I think we were pretty much spot on, and I think it was closer to the lower number. So the company developed from its early stages as an intellectual property type company, where what we did is went out to all the universities that would interact with us. We worked together with research scientists of a variety of types. This is a very multidisciplinary type of thing. And we developed very good intelligence on what worked and what didn't, what was important and what wasn't. And then roughly 3 years ago, we believe we found the path, and we started taking it. And at that point, we raised a considerable amount of money, and we changed the nature of the company from exploratory research to enablement of a particular idea. So it was a long path to get to the point where we thought we had something that we could build.
Now, as I understand, the model here is that you have this machine sitting at your headquarters, and that people basically set up the problem on their local machine and then use your machine remotely rather than buy your machine and run it itself. Is that correct?
You can certainly do that. It's configured to be remotely accessible, but it's not a requirement. In fact, it's probably true that most of the people who we've talked to are serious about using this machine have a requirement that it be physically present in their lab or in their data center.
So what does it look like?
So I have some pictures. Can we bring up the slide deck? So I'm just going to skip through some of the words and just show you it. So at the largest scale, what you see is something roughly the size of a large kitchen fridge, which is almost entirely made up of refrigeration equipment. So the vast bulk of this machine is for cooling. And the cooling requirements on this thing are quite extraordinary, as I'll show you. This thing sits inside a shielded room, which is a big metal room, which is a magnetic vacuum almost, at least for certain types of, certain frequencies of EM radiation. So this is what you would see if you were just to look at the outside of the machine. Inside this red thing, which is called a dewar, is an insert which is half fridge and half filtering. So the requirements on the actual chip are quite extreme. You have to be able to make it extremely cold. So we run these things at 10 millikelvin, which is 0.01 degrees above absolute zero. And just for a point of reference, the temperature of interstellar space is about 2.7 Kelvin. So this is very, very cold. Some people joke that, other than other fridges like this, these may be the coldest points in the universe. And they certainly are if there's no other intelligent life in the universe, because these types of situations don't occur naturally. The other thing is that the chip needs to sit in a magnetic vacuum, which is also a very stringent requirement. So a lot of the gadgetry you see, specifically down near the bottom of this thing, are very, very robust filters. So they filter out basically every bit of noise that you can with current technology to get the signals on the lines that are coming in and the ambient magnetic field down to very, very low quantities. So this 1 nanotesla in 3 dimensions across the whole chip is at or beyond the state of the art for magnetic vacuum technology. So one aspect of this project is we need to be able to build technologies that don't exist across a whole range of different endeavors. So it's not simple, it's very complicated and involves a lot of different branches of science intersecting. This thing at the bottom is the sample holder for the chip. So this is the one that we're actually connected to right now. We have a remote connection to this machine back at Burnaby set up. It has 128 pins around the edge. Each of these pins is connected to a trace, which then connects onto the chip itself, which is that thing in the middle. If you look very closely at the way that information is stored and processed in this chip, what you'll find is a series of metal traces on a silicon substrate. So the actual bottom part of the chip is the same as what you would use for any semiconductor process. What's on top are layers of metal interrupted by insulators. So this is not it's not your dad's processor. This is a entirely metal-based magnetic thing where all information is stored in the directions of current flows around loops and interaction between those things. This, what I'm showing you here, is what's called a qubit. So a qubit is the basic unit of information storage in a quantum computer, and that's what one of them looks like. This is an optical picture of the processor itself. Each of those little blobs is a qubit, and there are 28 of them in this particular design. And they're interconnected in a specific way that is related to the application that I'll be running for you. So this is the latest thing that we've demoed. It has 28 of these qubits. And what the demo that I'm going to show you later does is it does similarity matching between images. So this is a very hard artificial intelligence problem, and it turns out that quantum computers, their sweet spot is in the type of math that underlies certain hard vision problems and certain hard machine learning problems. So this is where we're placing the machines in the short term.
So we're going to see an actual demonstration up to Canada from
Yep.
San Diego. I love it.
Yeah.
Use that route a lot, different fiber. But anyway, I think that before we do that, could you just say a little bit about the breadth of applications that this could do, and then let's try the demo.
So it's actually quite narrow. The machine can be thought of most profitably as an analog computer. It's not exactly an analog computer. It's something novel that's never existed before, but conceptually, you can think of it like a special purpose chip that's designed to do one thing well. Ultimately, quantum computers will turn into a lot more than that, but when you do the first design iteration of any new technology, it always helps to focus what it does. So this particular chip, all it does are these problems related to pattern matching. Mm-hmm. So you can think of it as a special purpose pattern matching chip.
Good. Okay, well, let's fire it up and see if put it through its paces here.
So hopefully it'll work. It's been working every time I've tried it up to now.
Oh, we need to pray to the demo gods.
Yeah. Okay, so let me describe what you're looking at. So the way that this demo was constructed, and this is the way that we have to operate, is that it's unclear with any new technology, and especially one like this, where it will eventually find its home in business context. And the way that we try to answer that question is we go to eminent scientists, predominantly in industry, and we try to educate them as to what the thing is good at. And every once in a while, we'll find somebody who really gets it and is willing to work with us on building applications, prototype applications. This one was done in collaboration with Dr. Hartmut Neven at Google. He's one of the world-leading authorities on computer vision and does things related to object recognition in photographs at Google. So the idea here was to target what the chip is good at directly to an application in sort of a prototype format. So what we've done is built a system that uses the quantum chip to discriminate objects. So the way it works is that if I click on one of these query images, let's say this one, which as humans we can see is the Taj Mahal, and I ask it, are you the Taj Mahal? So what I'm doing here is I'm taking an image that has no labels whatsoever. There's no words associated with it. And what I'm doing is I'm going to compare that image to a bucket of images that are representative of the Taj Mahal, taken from different angles and things like this. So when I hit compare, what happens is a little bit of processing happens locally on this machine. It condenses the hard part of the problem into a little nugget and sends it remotely to the quantum computer in Burnaby. That then solves the underlying hard math problem and shuttles the answer back here. So this is actually happening right now. So we have a wireless link up to the internet, which then carries the signal back and forth to an actual quantum computer like I showed you in Burnaby, which I think is totally cool. Every time I do this, I can't help but smile. This is just a fabulous thing that you're actually building a machine that takes fundamental language of nature and uses it for some good use over something like the internet. It's just mind-boggling. Anyway, so the object image is the one on the left. And it found a match. And the way that it does the matching is that it extracts what are called interest points in an image, which is a completely classical thing, which you need good software, good vision software to do. And what the math problem under the hood is it tries to find a correspondence between the interest points in one image and the interest points in another by solving a hard math problem. And in this case, it's found a match. So what this says is that I could take that object, run it in an entirely automated way against a bucket of photographs, and automatically the machine will know that this thing is the Taj Mahal. So if you go back and you say, okay, that's great, what happens if you have a mismatch? So let's take a flower and we'll match it against Big Ben. So then this thing will now ask, picture of flower, are you Big Ben? Or do you have Big Ben in you? And hopefully, if everything is still working, the answer will be no. So you might ask, okay, so why do people care about this? And the answer is very simple. When you go to Google and you type for something you're looking for, you enter words. And words are these wonderful things that human culture has developed that are abstract tags for real objects. And sometimes when you're searching for something that's complicated or somehow unique, it's very difficult to describe that object in words. So for example, if I wanted to say, I wanted this particular table. So when I type words to describe this table, I can say, well, oval and 4 legs and all that. When I type that stuff into Google, what I'll get is generally a bunch of things that I don't want. It would be much better if you could actually take the table itself and jam it into your computer and say, okay, computer, this is what I want this thing. So we can't do that. What we can do is we can take photographs and use them as queries. So this thing is a first stage prototype of a system where you're going to be able to, instead of querying with text, you can query with objects. So you can go drag an image into a box, and all of the images that look like that thing will come up. You can drag even more complex objects, like, for example, what is the ideal business unit within my company to work on a certain project? I need 3 people with C++ programming experience. They have to make less than a certain amount and all this stuff. These complex combinatorial objects, you can define them, drag them, click, and everything that actually exists will be ranked in order of similarity. So this next generation of search is right on the sweet spot of what these quantum chips do well. So it's a very good match between the technology and ultimate business usage.
So then, let me ask you this. I mean, we're doing search now, and there's various kinds of image search using classical computers. So say it takes me 10 minutes or something to do the same kind of search with a classical computer. I mean, is the quantum computer just faster, or can it do kinds of qualitatively different kinds of search than the classic one? What is the advantage here?
It's the second, is that with this, there are already very fast algorithms for doing object comparison, but they have to make certain approximations to make them fast and tractable. What this allows is an additional level of complexity that remains roughly at the same speed. So your search will likely still take 10 minutes or maybe even a little more, but the quality of the match will be it will be massively improved. At least that's the hope. So what the chip does is allows you to feed more reality into what really is going on in an object search and not necessarily speed it up.
Okay. So one of the things that I learned over the years is as a place that bought everybody's weird supercomputer for 15 years, is to figure out what that was good for. We made those available to essentially everybody at any university in the country that had a good idea. There was a peer review to get just the best applications filtered out and so forth by a set of blue ribbon panel and all that. It seems to me that this is a perfect example where something like this would help you find other applications. Is that something that's feasible?
Yes, absolutely, and that's almost certainly where the first sales of the machines will go to, are to research entities who will provide the machine to a wide range of researchers to develop not only applications, but to do basic science, because there are ways to interact with this machine that probe the nature of the qubits and the couplers and the assemblies of qubits and extract wonderful things like entanglement measures. And so there's a way to use this machine which is divorced from applications, but still has a substantial following in the basic science community. And then there's also this application where if you don't care to know about any of that stuff, you can come in and build things like this. So I'm a big fan of the whole concept of opening the thing up as much as possible to anybody who cares to use it and making it easy to use even if you don't have the quantum physics desires or background.
So both Canada with the Canary Network and the US now with the National M-to-Rail Internet 2 have these centers. The TerraGrid, for instance, in the US is all the NSF supercomputer centers, and they have actually a garden of architectures across all of the centers. Are you talking to these on the academic side as well as on the business side? Because a lot of the innovation is actually in like the grad students, in a myriad of, you'd like to say, well, what can I do in genomics with this? What can I do in, I've got 1 billion images of stars now on these high density surveys. What could I be looking for?
Well, it's interesting that you mentioned those two examples because those are focal points for us. So in the bioinformatics, particularly where the information is discrete, and a lot of the problems are inherently combinatoric, which is what this thing does, like multiple sequence alignment and certain models of protein folding and things of this sort. We have had a long-standing relationship with some academics in this area who are now at Harvard, who have been working on building prototype applications like this. And in the star field stuff and cataloging of space-related images, we've had, again, a long-standing relationship with JPL. And they have this wonderful database of images, and they are desirous of building feature search. So there was a great article on the recent Mars mission in the USA Today yesterday. And one of the things they really care about is how many rocks are in a landing area. So it would be nice if there was an automated way to do feature detection like rocks, and then you could have a human come in and verify the count. So there are applications both in space images and in bioinformatics that we're looking at. In terms of the business end of things, most of our focus has been on the corporate side, but we have had interest coming from some of the big supercomputer centers to look at the performance of these machines, to see what state they're really at, come in and kick the tires, and then make a decision as to whether they'd want to acquire one.
Well, the last thing I'd just say about the supercomputer centers is forget the supercomputer centers. What's really valuable about them is the national set of end users who are that's what you're really trying to get access to, not the center itself. Although in the agencies, it'd be a little bit different.
Yeah, that's a good point.
So let me probe you just a little bit technically on this. There's been some controversy about, is this a full quantum computer? So you use terms like adiabatic. Is there real entanglement here? How do you see this within the spectrum of the universe of all possible quantum computers,
So it's known that there are several universal models of quantum computation, just like there are several universal classical models. The one that we have picked has significant advantages in that it's easy to implement with large qubits. So the technical jargon for the method is adiabatic quantum computing. It's one of the flavors of universal quantum computation. The chip is not capable of doing all of the things that a quantum computer can do because of our focus on this pattern matching application. So the way the chip was engineered, we picked something that was fundamentally hard, that was a good fit to the technology, and we just bare bones the whole architecture around that feature. It's possible to expand the technology to be able to do more things, but right now the thing is designed specifically to do pattern matching very well. So for example, some of you may have heard of other applications for quantum computing, such as code breaking, things of that sort. This chip is disabled in a way that makes those things not possible to run on it. it's possible that in the future we might expand the line if this particular project succeeds financially to include other types of processors that are able to harness nature in a way that will allow you to do these other things. But those are more long-term things, and it's certainly not our focus right now.
So a lot of the people in the audience here would be more interested not so much in the technology, but is this the start of a flourishing commercial market? What other companies do you see on the horizon? If you look out 5 years, how much growth the exponential stays flat for a very, very long time before it takes off. Are we out here, or are we just at the, takeoff? What do you think?
Well, one of the things that makes me hopeful that we'll live to see the takeoff of the exponential on the business side is that there's a huge push from the technology and science side for these machines to be built. So there are entire generations of people who are trained to understand the way that these things are supposed to be, the novel features that they will bring to the world. And I think that push is not going to go away anytime soon. This isn't like high temperature superconductors or fusion or something like that. This is something that's going to be pushed until it works. So that's one thing. The other thing is that there's strong evidence that the types of things it does well are in demand on the pull side. And I think that the big challenge is educating decision makers within companies that have these types of problems that this could potentially be important. So as an example, another article I was reading yesterday in the paper was about the increased baggage fees in airlines. So airlines and the US Air Force consume an awful lot of fuel. And if you take a moment to think about the logistics nightmare behind distributing and storing fuel and how much money that you might be able to save if you could do it better, that's another example of one of these combinatorial optimization problems that the Systroid chip does very well. Do the people who are running airlines know about quantum computing as a solution to their problem? Probably not. Is the education process going to happen immediately? No. But I think that certain visionary leaders in certain industry sectors will have their eyes open to new ideas that impact their business, and those are the ones who are going to buy the duct tape together research model and stick it with their scientists and say, hey, kick that around a bit and tell me what you think. So right now we're at the stage of trying to penetrate into those real early adopters who are willing to try something because of the desperation they face in their business troubles.
Great. So let's see, we've got a couple of minutes for questions. Are there questions out there? Yeah, got a microphone coming.
Cameron Lahian with Global Catalyst Partners. I guess I'm not sure if I understand the level of performance that you provide on the pattern matching that you showed. We have a company in our portfolio that does what you do, and something that is quite a bit more complex, and that of millions and millions of pictures on a PC. So they have very clever algorithms. So can you talk a little bit more about what you really are demonstrating in here?
Sure.
And maybe talk in terms of megaflops, teraflops or something, so that it would be a bit more understandable to me.
Okay, so the first issue about performance, so this is certainly not a demonstration of performance. This is a demonstration that you can actually run the system end-to-end. The people who we're working with at Google also have capabilities, as you're mentioning, where you have millions of pictures and you do the types of image sorts that you're discussing. The key difference between this and that is that with those, the requirement to do very fast search on a large amount of images requires that you sacrifice quality. This is just an absolutely true statement that when you're doing object match in images, when you have to do things quickly, you have to shortcut the process somehow. Often what will happen is in image search is that you can do very, very well on finding certain types of objects in images by spending an enormous amount of time up front. So at Google, for example, the software that Hartman is working on, is able to detect faces in photographs very, very well, very quickly. It does that because they spent a year using an enormous amount of computing cycles to train the software that is used to do that. So if you want the quality to be so-so, or if you're okay with that, which is true in many instances, or if you want to hone in specifically on one feature, conventional technology is good enough. If what you want is the quality that you get by that year-long process of training to find faces for any object, just like the human visual and perception system works, I can look out at a field of view and tag every object within a couple seconds. You just simply cannot do that today with conventional stuff. So what the chip does is it allows you to write new sorts of algorithms that you would never dream of doing today because they're too computationally intensive. And it's not everything. It has to be formatted in a specific way. But if you can do that, you can harness this vast computational resource. Now, the thing about flops. This thing is not a floating point processor. So it's very difficult. It doesn't even have clock cycles. It's like, so imagine you're trying to find the lowest point in a valley, and you have a ball, and you let the ball go. And the natural laws of physics tend to drive the ball downwards. If the thing can find the lowest point, it solves the problem. This processor is a lot like that. It uses a process called annealing. So basically, you let the thing go, and the natural laws of physics make the thing go down into its ground state, which is the answer you read out. So it's not at all, you can't compare it one-to-one with conventional processors in that way. In terms of the actual performance, though, you will be able to get quality of matching on large data sets that you simply cannot get with conventional processors, no matter how smart you are or how good your algorithms are. That's the hope.
Okay, well, I think we're out of time. Thanks very much, and thanks for the audience. Follow-up questions later.